Now, once you take the mass perspective, then immediately you have the notion of center of mass, center of gravity if you like to call it that. And when you take a probability density perspective, you have the notion of mean. Either of them is okay, they are equivalent. So, let us make a note of that. If we choose the mass perspective, consider the center of mass and spread around the center. Now, incidentally, as I said, the spread around the center in mechanics is often measured by a quantity called the radius of gyration. If we happen to take the density perspective, consider the mean and the variance. Now, we must of course assume that these quantities can be calculated, and we shall do that. It is possible that the variance be infinity. That is a subtle point. So, we are not always guaranteed of finite variance, and in fact, that is not a contradiction to what we have been saying so far. We are trying to find a lower limit to where the quantities go in the two domains simultaneously. So, of course, if the variance happens to be infinite, which it will actually in some situations, we shall simply say that is the worst possible case that we can encounter. Anyway, so let us consider, given this function x t, we will prefer to take the probability density perspective. So, we will think of P x of t and P x cap of omega as probability densities. And we will then write down their means. So, indeed, let P x t have the mean t 0. What would that mean? T 0 would then be integral t times P x t over all t from minus to plus infinity. Simple, a definition of mean. You will of course recognize the same definition to hold good for the center of mass here. Essentially, you are calculating the moment by choosing the fulcrum to be 0 and therefore, getting a different fulcrum or a point at which the moments are all balanced. Similarly, let P x cap omega have the mean omega naught, whereupon omega naught would be integral from minus to plus infinity omega p x cap omega d omega. Again the center of mass, if you like to look at it that way, in the frequency domain. Now, once we have the mean, and of course, just as a tongue in cheek statement, we assume the means are finite. Normally, they should be. In some pathological situations, we may have a problem. We are not looking at those pathological situations. So, assuming these means are finite, let us look at the variances. So, the variance in T would then be given by, and we will define it to be sigma T squared by definition. This would be T minus T 0 the whole squared times P x T integrated over all T. And similarly, we could talk about the variance in frequency. So, variance in angular frequency. Sigma omega squared is integral from minus to plus infinity omega minus omega naught the whole squared p x cap omega d omega. Once again, tongue in cheek, we are assuming these variances to be finite. In any case, here we do not have such a problem. Even if the variances are infinite, we will accept it. We will say that is the extreme and the worst case. So, whatever they be, finite or infinite, we accept them. Now, it is very clear, you see, if you look at a probability density, or perhaps if you choose to think of these as one dimensional masses, it is very clear that the variance is an indication of the spread. So, the larger the variance, the more the density is said to have spread around the mean. The smaller the variance, the more that density or that mass is said to be concentrated. So, now we have a formal way to define containment. In fact, we shall now make a very simple definition. We will say containment in that particular domain refers to the variance, or if you like, the square root of the variance, positive square root of course. So, let us put down this statement formally. We will say containment in a given domain refers to the variance in that domain. So, containment in time is essentially the sigma t squared quantity, and containment in angular frequency is essentially the sigma omega squared quantity. Now, we ask ourselves, how small can we make any one of these quantities for a function, for a valid function? And in a few minutes, we will be convinced that there is really no limit.